Hello everyone, today we're going to talk about the conditional probabilities. This notion is introduced each time we acquire an information, a partial information, on the result of a random experiment. To obtain this result, to obtain this partial information, let's consider a random experiment described by a probability space omega A P, with A the tribe and P the probability measure, because in the measure theory, a probability is defined as a measure. For instance, we can look at the shuffling of cards. We are looking to evaluate the probability of occurrence of a certain event A. Such as the last card is an ace, knowing that the event B has happened. For instance, the first card is an ace. Just an example among others you can choose. For obtaining an estimation of this conditional probability, we're gonna do n repetitions of the random experiment in independent and identical conditions. We're gonna do n repetitions of the random experiment in identical and independent conditions. Then we're going to consider the NB repetitions of the experiment that realized B, the event B. We can then think that the frequency n of A intersected with B over n of B, so the number of repetitions of both A and B happening divided by the number of repetitions of the event B happening. This is the frequency of realization of the event E among the NP repetitions of the experiment that realized B. The frequency of realization of the event A among the NB repetitions of the experiment that realized B. We can think that this frequency gives an estimation of the conditional probability of A. This gives an estimation of the conditional probability of A knowing B. Since this quantity NA intersecting B over NB is the same as NA intersecting B divided by N over NB divided by N, the conditional probability of A knowing B appears to be the division of the probability of A intersecting with B by the probability of B, because we have probability of A intersecting with B over P of B. We're going to adopt this definition of conditional probability. Then we can have the following definition, which is just what we already said. Let omega a p our probability space the probability of a conditional event. The probability of an event A knowing the event B denoted P of A knowing B is defined by the formula P of A knowing B equals P of A intersecting with B over P of B. With, of course, P of B being strictly positive, because the probability must be positive. And we don't want it to be equal to 0, because we can't divide by 0. Just need to add more space, and we're good to go. Just bear with me, it's going. Alright. The bar sign is also expressed as conditionally true. But I like to say knowing. It's more convenient. Let's fix now the event, the conditioning event D, whose probability is supposed to be strictly positive. The function defined by defined on our tribe A by this is also a probability on omega A, as we're going to show in the following proposition. Let omega AP our probability space let B be an event over time with a strictly positive probability. The function defined on A by this probability of A knowing B with A in our tribe of events is a probability on omega A. And that's it for today. If you want the proof, it will be in the next episode. Stay tuned. Catch you later.